let's say we're trying to find the volume of a cone. A cone with a circular base, whose base is, say, 10 centimeters in diameter, and whose height is 8 centimeters. Now, technically, we know the formula for the volume of such a cone. 1/3 pi r squared h. But let's try to figure it out, pretending we don't know that, because this is good skill to have. And I could certainly slice it with thin slices of width delta y like before, but let's illustrate that we also could just turn the cone on its side, draw it like this, and find the volume that way with thin slices of width delta x instead. So I'm going to make this distance from here to here be 10 centimeters. And that'll be the diameter of the base. The radius would be 5 centimeters. And this distance from here to here, let that be 8 centimeters. The volume can be found out as 1/3 pi r squared h. That's 1/3 pi times the radius is 5 and the height on its side is 8. 5 squared is 25. 25 times 8 is 200. The answer is 200 pi over 3. How could I derive this with integration? You can, if it's helpful, put an axis in here like an x-axis. If it's helpful, it's actually not absolutely necessary, but I think it's probably helpful. And imagine slicing this into thin slices that look about like this. Thin wafers, you might call them, like communion wafers or something, or really, really thin hockey pucks on their side. With the Riemann sum approach, we could approximate the volume of the thin wafer as if it's the volume of a cylinder, not a cone. Really thin wafer or thin hockey puck. A cylinder, pretending we know the formula for the volume of a cylinder, pi r squared times h. No 1/3 in front. Might say it's kind of silly to pretend you know one but not the other. Okay, humor me. Okay, we're pretending. Pi r squared times h, the radius, right there, you could call that maybe r of x, r for radius, but it depends on x. And what's the small width? How about call that delta x? So the small width here, hard to draw, of this thin wafer is delta x. So the volume is approximately, pretending the thin wafer is truly a cylinder, which it's actually not, because the sides are slanted. Can't do that. Like that or like that. The sides are slanted, so it's not actually a thin wafer, not actually a thin cylinder, but we pretend. It gets closer and closer to that being a good approximation as delta x gets smaller. Pi r squared times h. R of x is the radius, delta x is the height, though it's a height on its side. And then the total volume would be the sum of the little volumes. And now I'm not going to bother writing I goes from 1 to n. And I'm not going to bother with a subscript on the v, on the delta v, because in the end, all I'm after is an integral. That's going to be approximately a summation like this. Pi times r of x squared times delta x. Now you let delta x go to 0. And by definition, that's essentially the definition of the volume. The pi stays as it is. The r of x stays as it is. The delta x morphs into a dx by magic. Woo, woo. No, not by magic, by definition. And what's the interval of integration? I guess I didn't say that this was x equals 0 there, but I could have. X goes from 0 to 8. But to actually do the integral, I have to figure out r of x. Before doing the integral, which will be a fairly easy integral, let's do the infinitesimal version. Infinitesimal approach. Hang with me here. We'd write essentially this same equation in infinitesimal form. Change the deltas to d's and change the approximately equal to an equal to. dv equals pi r of x squared dx. Then find the total volume by adding up the little volumes. Then say to yourself, hey, if I'm actually going to do a calculation, I need to convert that to a definite integral, so do that. Get the same definite integral. Now let's do that integral. We need the r of x function. Quickest way to find it, I think, is with similar triangles. Take this cone and slice it with the plane of the paper, and just look at the top half of it, and you'll get two right triangles that are similar. This one having base x, this one having base 8. This one having height r of x, this one having height 5, the radius. And r of x divided by x is 5/8. That's similar triangles. You take the ratios of the corresponding sides, you get equality. So r of x is 5/8 times x. I have to square that function, multiply it by pi, and then integrate. Can do that in about 1 minute, I think. The volume is going to be the integral from 0 to 8. Pi times this function squared is going to be, well, let's write it as 5/8 x squared first. So I'm going to get 25 pi over 64 times the integral from 0 to 8 of x squared. An easy integral to do. 25 pi over 64 times 1/3 x cubed from 0 to 8. I think maybe I can avoid a calculator here. 25 pi times 8 cubed. 64 is 8 squared. The 8 squareds cancel, leaving you with an 8 to the first on the top. 25 times 8 is 200 pi over 3. Does that look familiar? Yes, it was the answer we got with the formula for the volume of a cone. 200 pi over 3. We got the right answer. Pretty cool, huh? You want to get skill at setting these things up. I think it's good to do both the Riemann sum approach and the infinitesimal equation approach. You'll see both in textbooks to help you set up the integrals and then do them to get the answer. The setting up is the main skill to get out of the chapter.